Alright, in this video we're going to talk about the basis of probability. So this begins chapter 9, which talks about probability. So in this section we're going to talk about the basics of probability. Okay. And here we're going to start with what they call the qualitative phrases that are in probability. So in this case here we're going to look at some of the categorical phrases that are in this particular chapter or in this particular section. Okay, in this case here, words and phrases such as impossible, unlikely, likely, and certain to occur are qualitative phrases that we often use to informally characterize the level of uncertainty in a situation. So, students in this case should be able to describe events as likely or unlikely and discuss the degree of likelihood using such words as certain, equally likely, and impossible. So like in this first example, you'll see for each one we want to decide whether the situation is impossible, unlikely, likely, or certain to occur. So in part A, you see that you will win the lottery, which is, in this case, is going to be unlikely because of the fact that usually probability for lotteries are very slim. The outcome for winning will be very small. Your pet will learn how to build a spaceship. That would be impossible. Okay. And you will stay awake during the lecture. That is likely to occur. Okay? Likely to occur. So, in elementary school, students initially engage in explorative activities such as flipping a coin, spinning a spinner, or drawing marbles from a bag, and use terms such as always, maybe, sometimes, never, likely, unlikely, certain, and impossible to describe the chance that a situation will occur. So that's basically what the definition of what probability is. It is just going to be the chance that an event will occur. Okay, and we use those phrases. So in this example here, example 2, a teacher shows his class a bag containing 3 blue marbles, 15 red marbles, and 72 green marbles. The teacher randomly selects a marble from the bag. Use the word impossible, unlikely, likely, or certain to describe how likely it is that the teacher will draw a blue marble, a red marble, then a green marble. So that's parts A, B, and C. And the solution for that is right here on this next slide here. In this case, in part A, there are a few blue marbles in the bag compared to the total number of marbles in the bag. So the teacher is unlikely to draw a blue marble. Okay. And in part B, for drawing a red marble, we said that there were 15 marbles. That means that's less than half of the marbles in the bag are red marbles. So the teacher is, again, unlikely to draw a red marble. And then part C, drawing a green marble. In this case, we have 72 green marbles that were in that bag. That means that's more than half the marbles in the bag. So, that teacher would be likely to draw a green marble. Now this is in your book on page 504, problem number 11. It says here, in a bag of marbles, 1/4 are blue, 1/6 are green, 1/2 are yellow, and 1/12 are black. If you randomly draw one marble from the bag, which color is most likely? Well, by looking at this, the fraction 1/2, that means half the marbles in that bag are yellow. That number, that 1/2, is more than 1/4, 1/6, and 1/12. So more than likely that you would draw a yellow marble, because there's 1/2, half the bag, half of the marbles in that bag are yellow. Okay. Alright, next we're going to look at the language of probability. The language of probability. Here's a few formal vocabulary words that are related to probability. So here, an experiment is a procedure in which something happens, but the result is not known in advance. So in this case, we can think of things like tossing a fair coin, or rolling 2 dice, or spinning a wheel, or selecting a card from a deck of 52 playing cards. Those would be experiments. An outcome is the result of the experiment. So if you toss a fair coin 3 times, we can get the result from that. The sample space is a set of all possible outcomes of an experiment. So if you're tossing a fair coin, you're going to end up with either heads or tails. If you're rolling a fair die, a single die, then it's going to be 1, 2, 3, 4, 5, or 6. An event is a collection of outcomes. By convention, the letter S, or capital S, represents the sample space, and the other capital letters like A, B, C, and so on would represent events. Okay. So in this case here, if we go on here, an experiment consists of spinning the 1 through 5 spinner in figure 1 and recording the number to which the arrow points, as you can see here in this particular problem. The sample space is, in this case, S is equal to 1, 2, 3, 4, and 5. A is equal to 1, that's the event in which the spinner lands on 1, and B, which is equal to the numbers 1, 2, that's the event in which the spinner lands on a 1 or 2. Capital letter A is an example of a simple event because it consists of exactly one outcome. Experiment B, capital letter B, is an example of a compound event because it consists of more than one outcome, as you can see here. So, in this example 4 that I'm going to show you here, you're going to refer to the 1 through 5 spinner in figure 1 and consider the events A equaling to 2, 4, and B equaling to the elements 1, 4. Part A, if the spinner points to 3, did event A occur? And explain your answer. And part B, if the spinner points to 1, did event B occur? And explain your answer. Alright, so in this case, here to answer part A of that question, A is the event that the spinner points to 2 or 4. The spinner landed on a 3, so event A did not occur. Now in part B, B is the event that the spinner points to 1 or 4. In this case, the spinner landed on a 1, so event B did occur. Now here we're going to be talking about how to use numbers from 0 to 1 to represent probability. Okay. The expression P with the E in the parentheses represents the probability or likelihood or chance that event E will occur. So here you can quantify the probability with a fraction, a percent, or a decimal number. So here, if event E is impossible, then we say that the chance of E occurring is 0. And that's the notation here. The probability of event E occurring is equal to 0. And if event E is certain to occur, then we say that the chance of E is 1. That is, the probability of event E is equal to 1. We call that a certain event. And of course, if it's equal to 0, then the probability would be of event E equaling to 0. That's called an impossible event. And if we are uncertain whether E will or will not occur, then the probability of event E would be between 0 and 1. And now next we're going to look at this right here. The closer the probability of event E is to 0, the less likely that event E is to occur. And the closer the probability of event E is to 1, then the more likely it is that E will occur. So here's that concept map here. As you can see here, if it's close to 0, it's very unlikely. If it's closer to 1, then it is very likely. And keep in mind that the probability cannot be negative, meaning you cannot have a negative probability for an event, and your probability value cannot be bigger than 1. Okay. Now let's talk about experimental probability. Suppose you observe that event E occurred F times when you repeat an experiment N times. Here, the experimental probability that event E will occur is the fraction F over N. And here, the experimental probability depends on the observations. So, in example 5 here, an experiment consists of rolling 2 standard dice and then multiplying them to shown on the top of each die. For example, if one die shows a 4 and the other die shows 2, then the outcome is 4 times 2 equals 8. So in part A, what is the experimental probability of getting a 3 or a multiple of 5? And then part B, suppose you repeat this experiment 60 times based on the experimental probability in part A. How often would you expect to get a 3 or a multiple of 5? So here is our solution for part A. The event of getting a 3 or a multiple of 5 is going to be this: 3, 5, 10, 15, 20, 25, and 30. Okay? So those represent multiple of 3 and multiples of 5. Here we're going to roll the dice 32 times, and these are the outcome, the actual outcome in this particular table, as you see. And here's the frequency table that is shown here. The number of times that event E occurred and the number of times that event E did not occur, based on this table at the top. So in this case here, F is equal to 10 and N is equal to 32. Then the experimental probability of getting a 3 or a multiple of 5 is 10 over 32, which is approximately 31%. And then part B, based on the results in part A, we expect event E will occur 10 times for every 32 rolls. So here we have a proportion here. 10 over 32 is going to be equal to N over 60. I'm sorry, A over 60. A is going to be the number of times we expect event E will occur when we roll the dice 60 times. So if you're doing a cross multiplying here, 32 times A will be 32A, and then 10 times 60, which will be 600. Then you have to divide both sides by 32 to solve for A, which will be 18.75, but we're going to round it up to 19. So based on the experimental results, we expect the event to occur 19 times when we roll the dice 60 times. Okay. Now let's take a look at problem number 3 on page 503. It says a student repeated an experiment of randomly drawing one letter from a bag that contained 6 letters and recorded the frequency shown. The frequency table shown, as you can see here. Here's the outcome, and that's the frequency. GRADES. That's each individual outcome, and each letter has the frequency where that letter, how many times that letter was drawn out of the bag. Here we're going to find the experimental probability of each event. Like in part A, for R. So here we're trying to find the probability of drawing the letter R. Now if you look at the table, R was drawn out of the bag 5 times. And then that's going to be divided by the total frequency. So here I need to add these individual frequencies together. So here if I add 4 plus 5, that's 9, plus 1 is 10, plus 7 is 17, plus 3 is 20, plus 5, that's 25. So in this case here, the probability of event R will be 5 out of 25, or if I reduce that, it would be 1/5. Now I'm not sure if they want this as a decimal, but if they want that as a decimal, as a percent, you have to do, in this case, 1 divided by 5 times 100. Because by doing 1 divided by 5, you're only going to get the decimal. So for the percent, you have to multiply by 100. So it ended up being 20%. So in this case here, the probability of drawing the letter R will be 20%, or 1 out of 5. Now part B is E and A. But it's just saying the probability of drawing an E or an A. Let's look at the letter E. It's drawn 3 times out of 25. And then we have to look at A. A is only drawn 1 time out of 25. So let's add those two together. 3/25 plus 1/25. That's going to be 4 over 25. Now if I do 4 divided by 25 and then multiply by 100, it will be 16%. So the probability of drawing an E or an A would be 16%, or 4 out of 25. Okay. Alright, next is problem number 6 on page 504 in your textbook. A bag has B blue marbles, Y yellow marbles, and G green marbles. There are N marbles altogether. An experiment consists of randomly drawing a marble from the bag. What does each fraction represent? Well, let's take a look at part A. It says Y over N. Y is the number of yellow marbles, and there are N marbles altogether. This represents the probability, and I'm not just going to abbreviate here, the probability of selecting or randomly drawing a yellow marble. But in this case, you have to kind of spell it out, write it out. I'm not sure how they want it, but you might need to write it out by saying the words probability of selecting or randomly drawing a yellow marble. And in part B, we got G over N. G represents the number of green marbles. So this will be the probability of selecting a green marble. And then part C, B plus G in parentheses divided by N. So we're talking about a blue and a green marble. But in reality, it's going to be the probability of selecting a blue or green marble. Because we're going to add the two probabilities together. Okay. So that's what each of those fractions represent. Alright, next we'll talk about short-term and long-term behavior of experiments. So in this case here, it is likely the 1 to 2 spinner in figure 2 will land on 2, as you can see there. So here we expect the spinner to land on 2 in 75% of the spins. Okay. Now later on we're going to be talking about expected value when we get to section 9.3. So in this case here, table 9.1 displays some experimental results generated by a computer, where N is the number of spins, F is the number of times the spinner landed on 2, and F divided by N is the fraction of times the spinner lands on 2. And as you can see here, this is the outcome. Okay. Now in figure 3, this shows the graph of the ordered pairs F, N, and F divided by N. That fraction F divided by N is always a number from 0 to 1. It's never negative, and it's not going to be greater than 1. So that's what this looks like. And next, small values of N represent short-term behavior, and large values of N represent the long-term behavior. Here, that graph that I showed you reveals F divided by N fluctuates wildly for small values of N, but the number F divided by N tends to hover near our expectation of 0.75 for large values of N. Okay, so going back here, you can see it's fluctuating for smaller values of N, which is this horizontal axis. But as we get further and further and further, do more experiments of this, do more spins, it's going to get closer and closer to the expected value of 0.75. Okay. The data in table 9.1 and figure 3 suggests experimental results are unpredictable for a low number of repetitions of an experiment. That's F divided by N, that varies from 0.680 to 0.831, but are more predictable for a large number of repetitions. F divided by N consistently hovers near 0.75. Okay, so the more experiments you do in this particular situation, then in this case here, you're going to get closer and closer and closer to that actual expected probability. So in this case here, for larger N, we would expect to see the graph settle more closely to 0.75. Okay. Now let's take a look at problem number 4 on page 504. It says here the table shows data for Raj, Gina, and Taylor. And there's that table right there where you got the number of times E occurs and then your N. For each student, determine the experimental probability that E occurred. Okay. Now I'm going to have to bunch this up a bit here. So here for Raj, his probability of event E is this, as a fraction. The number of times E occurred is 68 and then 120. So if he tossed up, well, let's say he tossed up their coin. and then want to find out the number of tails. He got the tail 68 times out of 120 tosses. It could be anything. Now, for Gina, the number of times her event occurred was 147, so the probability of event E was 147 out of 250. And then for Taylor, her probability for event E occurring, that's 260 out of 400. Okay. Now I'm going to have to put the percentages here for each one of those because I'm not sure if they want the percentages here. Okay, so let me clear this out. Raj was 68 out of 120. So if I do 68 divided by 120 times 100, because I want it as a percent, I'm going to say to the nearest whole percent, about 57%. So I'm going to put 57% here. And then for Gina, it was 147 out of 250. So I'm going to do 147 divided by 250 times 100. I get 58.8. So this will round off to 59%. And then for Taylor, 260 divided by 400 times 100. Well, it's exactly 65%. Okay. So those percentages represent the probability for each one of those as a percent. Now, part B, which experimental probability seems like the best estimate for the probability of event E? And I would say this one right here. And that's because of the larger n right here. So that 260 over 400 would be the best. And that's due to the larger value of n. And then part C, how could these results be combined in some way to obtain a potentially better estimate of the probability of event E? So pretty much I'll add these numbers together, the number of times that E occurred, and then add all the n's together. So in this case here, the numerator for the probability of event E, I'll do this down here. That's going to be, I'm going to add 68 plus 147 plus 260. That's going to be divided by the denominator, the sum of 120, 250, and 400. So if I add this numerator, that's going to end up being 475 divided by n. The 120, 250, and 400 added together will be 770. And if I do 475 divided by 770, multiply that by 100, round that off to the nearest whole number, percent, it'll be approximately 62%. So basically all I did was just add all the number of times that E occurred for all three and your n values for all three. Divide the total number of times E occurred by the total number of n. That would be your probability. Okay. Now let's talk about the law of large numbers and the theoretical probability. So here the values of f divided by n in figure 3 tends to settle near the number 0.75 for large values of n, as you can see in this particular graph given to you. Next. Okay. So this supports our hunch that the number between 0 and 1 that best quantifies the chance the 1 in 2 spinner lands on 2 is 0.75. The theoretical probability is the expected long-term behavior of experimental results. So the theoretical probability of the arrow landing on 2 for the spinner in figure 3 is 0.75. The law of large numbers states that the fraction of times an event E occurs when an experiment is repeated n times approaches a fixed number as n increases. So as we let n get bigger and bigger and bigger, then that means the fraction will get closer and closer to that experimental or that theoretical probability value. So the law of large numbers, that fixed number is the theoretical probability that E occurs. So here the law of large numbers is this. Suppose event E occurs F times when an experiment is repeated n times. As n increases, the fraction F over n approaches the theoretical probability that E occurs, as I stated earlier. So in example 7, an experiment consists of drawing one marble from a bag, noting the color, and replacing the marble. Two students, Shauna and Layla, performed this experiment. Shauna picked a blue marble 48 times in 200 tries. Layla picked a blue marble 95 times in 500 tries. So in part A, which fraction, 48 over 200 or 95 over 500, do you prefer as an estimate of the probability of drawing a blue marble? And in part B, how can you combine the results to obtain another estimate of the probability of drawing a blue marble? So, here's the solution. The experimental probability of 95 divided by 500 is 0.19. That's preferred because of the greater number of repetitions. That denominator, 500. And then part B is this. By combining the results, we observe that a blue marble is picked 48 plus 95, that's equal to 143 times, in 200 plus 500, which is 700 tries. So 143 over 700, which is approximately 0.20, is another estimate of the probability of drawing a blue marble. Now we do not know which estimate, the 48 over 200, which is 0.24, 95 divided by 500, which is 0.19, or 143 over 700, which is approximately 0.20, is more accurate, but the law of large numbers suggests the estimate of 143 over 700 is preferable. Okay. A student flips a fair penny several times and records the number of tails in the table. The letter N represents the number of times the student tossed a coin. One table shows experimental results generated by a computer, and the other shows phony data generated by the author. And then the question would be, identify the table with the experimental results and explain how you decided the other table consists of phony data. Okay. Now, this is what table A looks like, and these are the results here. I'm going to do each one of these individually and just record the probability values there above those columns here. So like there were n tries and only one tail, 1 divided by 10, that would be 0.1. Here we got 855 tries, 396 times was tails, so 396 divided by 855. That would be approximately 0.46. Here I'm writing these as decimals here. Then the next one was 1,724 trials, and 840 tails, 840 divided by 1724 would be approximately 0.49. And that last one, I'm going to do 2588 divided by 5268. That would be 0.49. Now for table B, 10 trials, 4 tails, 4 divided by 10, 0.4. This one, 748 trials, 300 tails, 300 divided by 748, that's going to be 0.40. And 1329 divided by 1832, that's going to be approximately 0.73. Rounding them off to 2 decimal places. And then the last one, 2764 divided by 4368 is approximately 0.63. So by looking at this, I want to identify the table with the experimental results. It will have to be table A, because if you look at this, 0.49 is close to 0.50. The actual probability of drawing a tail is 0.5. And these two right here are close to 0.5, so table A would be the experimental results. Table B will have to be the one with the phony results here. Alright, next we'll look at practical applications of the law of large numbers. We'll just look at just this one thing and then we'll go on to something else here. How would you find the probability that if you toss a tack, then it lands point down? Or the probability that a newly manufactured light bulb is not defective? In this case, we cannot calculate theoretical probabilities for these types of situations, but we can reliably explore, or, well, reliably estimate theoretical probabilities with experimental probability. Okay. So how do we interpret a probability? That's the next thing we'll look at here, interpreting a probability. So, in this example, we can interpret a probability like this. Here's example 8. An experiment consists of spinning a spinner with the colors blue, green, and yellow. The teacher states that the theoretical probability of the spinner landing on blue is 35%. So what does this mean? Here it is. If you spin the spinner many times, you can expect 35% of the spins to land on the color blue. So for example, let's say you spin the spinner 856 times, then you would expect the spinner to land on blue approximately 300 times. So if you take 35%, multiply that by 856, 35% will be 0.35 times 856, that's approximately 300. Here's problem number 9 on page 504. And it says here a bag contains 450 blue and yellow marbles. The probability of drawing a yellow marble is 36%. How many blue marbles are in the bag? Well, let's find out how many yellow marbles are in the bag. 36% as a decimal will be 0.36. You take 36 divided that by 100, you'll change that to a decimal. And that's going to be multiplied by the number of blue and yellow marbles in that bag, 450. So 0.36 divided by, times 450. 0.36 times 450. That would be 162. So we know that there are 162 yellow marbles that are in the bag. But how many blue marbles are in the bag? Well, If there are 450 blue and yellow marbles in the bag, and we found out that there are 162 marbles in the bag, 450 minus 162 would be 288. So there are 288 blue marbles in that particular bag. Okay. All right, next we'll look at problem number 20 on page 505. In a fourth grade class, 75% of the students are boys. You randomly select a student from this class. What is the probability that the student is a boy? Well, that's already given to us here. The probability of selecting a boy. And we're told that 75% of the students are boys, so the probability of selecting a boy is obviously 75%. Okay. All right, next we'll talk about equally likely outcomes. There we go. Equally likely outcomes is the next thing we'll look at. So let's say we let S equal to x1, x2, all the way out to x sub k. That's going to denote the sample space. If the outcomes are equally likely, then all outcomes have the same chance of occurring. That's the definition of equally likely outcomes. That means that all your outcomes will have the same chance of occurring. Mathematically, this means that the probability of x1 will be equal to the probability of x2, equaling to and so on, equaling to the probability of x sub k. And this is where P of x represents the probability of outcome x. So rolling a pair of die or tossing a pair of coin, those produce equally likely outcomes. Each will have an equal chance of being selected or coming up. So here, the following is a classical result that plays a large role in probability in the elementary math curriculum. And this is how we calculate the theoretical probability of event E when the sample space consists of equally likely outcomes here. Suppose all outcomes in an experiment are equally likely, then the theoretical probability that event E will occur is denoted P with the E in the parentheses, is given by this. The probability of event E, that's equals to the number of ways that E can occur or event E can occur, divided by the number of equally likely outcomes in the sample space. So in example 9, an experiment consists of rolling a standard die and recording the number on the top face of the die. Determine the probability of rolling a 1 or 5 in part A and part B an even number. So here the die is fair, which means all outcomes S, which is 1, 2, 3, 4, 5, 6, are equally likely. And in part A, we're going to let A represent the event of rolling a 1 or a 5. So that means A will be this 1, 5 in braces. There are 2 ways that event A can occur and 6 equally likely outcomes in the sample space. So the probability of event A is going to be 2 divided by 6, or 2/6, which we can reduce to 1/3. And then part B, let B represent the event of rolling an even number. Then B will be 2, 4, and 6. There are 3 ways that B can occur and 6 equally likely outcomes in the sample space. So the probability of event B occurring will be 3 divided by 6. 3/6 will be reduced to 1/2. Let's take a look at this example, number 12. An experiment consists of tossing 2 standard dice and recording the sum of the number of dots shown on the top face of each die. Determine the probability of rolling in part A, a 5, and in part B, a 3 or a 5. So in this case here, this is what table 9.3 represents over here. The possible outcomes here of rolling 2 fair dice. In part A, there are 4 possible ways to obtain a sum of 5. In this case, this diagonal represents how many ways you can get a 5. A 4 and a 1, a 3 and a 2, 2 and a 3, and a 1 and a 4. There are 4 ways out of a possible 36 ways, as you can see here, because we're rolling 2 fair dice. So that probability would be 4 divided by 36. Probability of rolling a 5 would be 4 over 36. We can reduce that to 1/9. And then for rolling a 3 or a 5, there's only 2 ways of rolling a 3, and there are 4 ways of rolling a 5. So if I add 2 and 4 together, that would give us 6 ways of obtaining a 3 or a 5. So that probability would be 6 over 36. So the probability of rolling a 3 or a 5 would be 6 out of 36, or 1/6. Okay, take a look at problem number 36. Now, in this case here, a jar has 6 green marbles, 3 blue marbles, and 5 yellow marbles. An experiment consists of randomly picking a marble from a jar. So in part A, what is the probability of picking a green marble? So let's say the probability of selecting a green marble out of the jar. And it says here we got 6 green marbles here. So I know that numerator is 6. Now I need to know how many marbles altogether are in that jar. So if I add 6 and 3, that's 11. Plus the 5 yellow marbles, that's going to be 14 marbles altogether. So that denominator there will be 14. So this would be 6 divided by 14. But if I reduce that, that's going to be 3/7. And if I do 3 divided by 7 times 100, this will be approximately 43%. And then what is the probability of picking a green or yellow marble? So the probability of a green or yellow marble. Well, I know there are 6 green marbles out of 14, so that's 6 divided by 14. And here I'm going to add to it the number of yellow marbles. In this case, there are 5 yellow marbles out of 14. So this will be 5 divided by 14. So in this case here, if I do 6 14ths, add that to the 5 14ths, I'm going to get 11 14ths. And 11 14ths, if I write that as a percent, 11 divided by 14 times 100, this will be approximately, to the nearest whole percent, 79%. So the probability of picking a green or yellow marble would be 11 out of 14, or 79%. Okay. Next, we'll look at this example, problem number 43 on page 506 in your book as well. The table shows the number of minutes customers waited in line at a bank during the lunch hour and the corresponding frequencies, as you can see. Now, what would be, we want to find the probability of each event. So starting with part A, we want the probability of a customer who waited 4 minutes. Okay. So the probability of someone who waits 4 minutes, if you look at the table, 4 minutes waiting, 3 people waited 4 minutes. Now let's add up what the total frequency is. 7 and 10 is 17, plus 4 is 21, plus 3 is 24, plus 2 is 26, plus 1 is 27. So the total is 27. And for 4 minutes, 3 people waited 4 minutes out of 27. So 3 divided by 27, well, let's write that in simplest form. This will be 1 over 9. And if I do 1 divided by 9 on the calculator, multiplied by 100, this will be approximately, I'm going to say 11%. And I'm not sure how many decimal places, but here it's going to be to the nearest whole number. It'll be 11. But you round to whatever decimal place they ask for in the WebAssign software. Part B, a customer waited 3 or 4 minutes. We want that probability. For the probability of 3 or 4 minutes. So that means I need the probability of 3, and I'm going to add that to the probability of 4. Well, for 3 minutes, that was 4 people waited 3 minutes. So this will be 4 out of 27. Plus, well, probability of 4, that was let's say 3 out of 27. That way, we'll have the same denominator. So 4 27ths and 3 27ths will be 7 over 27. And I'm going to do 7 divided by 27 times 100. Which is approximately, to the nearest whole percent, 26%. So the probability that a customer waited 3 or 4 minutes would be 26%, approximately. Part C, a customer waited less than 4 minutes. Less than 4 minutes. Less than 4 means we cannot include 4. We only can include 1, 2, and 3. Not 4, because 4 is equal to 4. Less than 4 means 3, 2, and 1. So I've got the probability of 3, the probability of 2, and the probability of 1. So the probability of 3, we already know that's 4 over 27. The probability of 2 is 10 over 27. Here, 2 minutes, 10 people waited out of 27. And for 1 minute, here's 1 minute, 7 waited out of 27. Add those probabilities together. 4 plus 10 is 14, plus 7 is 21 out of 27. To the nearest whole percent would be 78%. Now that 21 over 27, I think that can be reduced by dividing the numerator and the denominator by 3. You'll get 7 over 9. 7 ninths. And then finally, part D, a customer waited 5 or more minutes. So we got to look at the probability of exactly 5 and add to it the probability of 6 or more. So in this case here, I'm going to need to move this up. The probability of exactly 5 would be 2 out of 27. The probability of 6 or more was 1 out of 27. So this will end up being 3 over 27. Divide the numerator and the denominator by 3. That would be 1/9, which is approximately 11%. if you convert that to a percent by doing 1 divided by 9 times 100. Okay. So that was problem number 43 on page 505. Okay. Alright, next we'll look at the sum of probabilities here. The sum of probabilities. In table 9.5, it shows the outcome and probabilities for the 1 through 3 spinner in figure 4, as you can see here. That means the sum of those 3 probabilities, probability of event 1 plus the probability of event 2 plus the probability of event 3, which was 0.20 plus 0.30 plus 0.50, that total is equal to 1. Okay? And that's always going to be the case. So here, if the sample space of an experiment in S is this, x1, x2, all the way down to up to x sub k, then the probability of event 1, x1, the probability plus the probability of x2, plus and so on, all the way up to the probability of x sub k, must be equal to 1. And that will always be that case. The probability will always be equal to 1. Okay. An experiment consists of spinning the 1 through 3 spinners shown and recorded in the outcome. Okay. Now, this represents 73 degrees. It's hard to see. And this represents 107 degrees here. And this is problem number 1 on page 503. Now in this case here, we're going to list the sample space. Well, the sample space consists of these numbers, 1, 2, and 3. And then determine the probability of each outcome. Okay, so I'm going to need to write this down here. So this is going to be part B here, where you got the probability of rolling a 1, but spinning a 1. We're going to use these degrees right here. This is 73 over, and I need to explain something right here. The number of degrees in a whole circle, that's always going to be 360. Okay, I don't know if you learned this in one of the chapters that deal with geometry, but in a circle, the degree measure is always going to be 360 degrees. So it'd be 73 over 360 for the probability of spinning a 1. Now, if you do 73 divided by 360 on the calculator and multiply it by 100, you'll get approximately to one decimal place 20.3 degrees. And then the probability of event 2, or spinning a 2, this says 107 degrees, so it'll be 107 over 360. And then this case here, 107 divided by 360 times 100 would be 29.7 degrees. percent. And the probability of spinning a 3, well, they don't give the degrees here, but I know this. If I know what 73 is, and if I know this 73, that's 107, add those numbers up, that's going to be 180. The whole circle is 360, so subtract 180 from the 360, you'll get 180 degrees. So this will be 180 divided by 360. And if you do 180 divided by 360, that's going to be 50 degrees. 50%. 180 divided by 360 times 100, that would be 50%. So that's part B. Now in part C, they want you to verify that the probability of the event of spinning a 1 plus the probability of spinning a 2 plus the probability of spinning a 3 has to be equal to 1. Okay, this is what I'm going to do. I'm going to bring this down here. Well, the probability of event 1, and I'm going to use these fractions here, that's 73 over 360. Plus the probability of event 2, that was 107 over 360. Plus the probability of event 3 occurring, spinning a 3, 180 over 360. Those sums have to be equal to 1. Well, the denominators are the same, I can just add the numerators together. 73, 107, and 180 does give me 360 over 360, which is 1. 360 divided by 360 is 1. So I've verified that the sum of those three probabilities do equal to 1. Okay, now let's look at this other example. This is problem number 37 on page 506. A 1 through 3 spinner has the following properties. The probability of event 1 is 0.3 and the probability of event 2 is 0.25. And here we want to calculate the probability of event 3. Well, I know that the probability of event 1 and the probability of event 2 and the probability of event 3 added together does equal to 1. I know what the probability of event 1, that's 0.3, plus the probability of event 2, that's already 0.25, so I want the probability of event 3. And that sum has to be equal to 1. In this case, 0.3 and 0.25 added together will be 0.55. And then plus the probability of event 3 must be equal to 1. And then to find out what the probability of event 3 is, subtract 0.55 on both sides. Here I'm solving an equation. So the probability of event 3 will have to be 1 minus 0.55 will be 0.45. So the probability of event 3 occurring will be 0.45. Okay. Okay, I'm going to momentarily stop right here with section 9.1. There is a part 2 to this video, so do be on the lookout for part 2 of this particular video for section 9.1. Okay, this will be continued on another video, so be on the lookout for that. So for now, we'll pause here and pick up with that on the next video.